All right. Actually, I should check and see who's here. Make life easy for me. Ryan's here. Amanda's here. Michael. Yep. Alexis. Chad's here. Bridget, definitely. Yeah, Bridget's here. Hannah. Is Hannah here? Reagan. Is it Diksha? Yeah. Austin. Zach is here. Now Reagan's here. Sally, Cassie, Michaela, Jerry. Yeah, there's Jerry. Jaren. Haley. There she is. Tessa, Edward, James, Tori, Sade, and... Okay, so I see everybody but Hannah. Is that accurate? Well, I saw everyone. Jared just walked out. Oh, excellent. I should have known it was going to disconnect when my tablet froze right after connection. Let's try again. Okay, today's experiment is going to be dealing with energy and how energy can transform back and forth between types of energy. So the types of energy we're going to be looking at are two forms of potential energy. Potential energy is energy something has because of its configuration. It's actually not energy of a specific object, but it's an energy of a system. For instance, you can have gravitational potential energy, which is potential energy between two objects because of the gravitational force. Or you can have, well, electromagnetic potential energy for a similar way. So these are what we're going to be looking at. Hopefully now it's going to show up. Yay. Now I'm a little afraid to change, but you guys got to do what you guys got to do here. So I have what I think, obviously this is written by me, so I think it's really, really astute, but a little history of energy here in the lab guide. Some interesting things are, while the first topic or idea of energy came from Aristotle way, way back, once again, Aristotle long before the time of Christ, the concept was rather nebulous. And in fact, energy and momentum were not distinguished as different things back in Aristotle's day. It was just kind of like the idea that you have to have something to make something move. But you move forward in time, and you get to 1829, when the term kinetic energy was coined. And so kinetic energy, that's energy something has because it's moving. Then you get to 1853 when they had the term potential energy. Energy something has because of its configuration. And then the final, I guess I shouldn't say nail in the coffin, that's the wrong one. But the final piece to make energy extremely important to us came in 1916 when Emmy Noether came up with a mathematical theorem. The thing I love about mathematics is it's unlike science where everything's kind of like, well, we tested this and works, we tested that and it works, but we still don't know if it's correct. When you're doing math, you have clean equations. If your premises are correct, you know the answer's correct. And what she was able to show mathematically was that we can't create or destroy energy. That our universe has a fixed amount of energy. It can be transferred from one thing to another. So, for instance, we can have solar panels that will take solar energy and transform it into electrical energy. But we can't just create electrical energy. It's always a transfer process. So that key of energy conservation is really one of the fundamental important things we use in science. Now, the definition of work, we've seen it in class from yesterday. This way here is usually the preferred non-calculus way of writing it. The force parallel times the distance moved. Force parallel to the distance moved. I put the calculus version there. The work-energy relation is the important beginning point of how I defined energy in class yesterday. The working definition that I gave you for energy was the ability to do work. And this work-energy relation, or work-energy theorem as their textbook calls it, is that the change in kinetic energy is equal to the net work. So that if you do work on something, its kinetic energy changes. But it has to be the net work. So let's say, as an example, that I were to push this thing at a constant speed. The kinetic energy is the energy in motion, and I work out right here in math that kinetic energy is, and I'm going to just cut out the C part, because as it says below, by convention, we set that constant equal to 0. So the kinetic energy is 1/2 mv squared. So if I'm moving at a constant speed, the kinetic energy is staying constant. But I am putting a force on this. It's moving parallel to my force. I'm doing a work. But if the kinetic energy is staying constant, what does that tell you about the net work? 0. So the net work is 0. If I did work, something else had to do a negative work to counter it. And of course, what force was doing the negative work to counter my positive work? Friction. Right. So we have the idea of kinetic energy, 1/2 mass times speed squared, that we're going to be dealing with in the final part of today's lab. Then we have the potential energy idea, the idea that you can have the ability to do work because of configuration. Potential energy only applies to certain forces. Forces that are called conservative because they're forces that if you do work against that force will return the work. And examples of conservative forces include springs and gravity. There are some others, but those are the ones we're looking at today, springs and gravity. A spring, if I stretch the spring and I let go, it comes back. If I compress and I let go, it pushes back out. Now our springs that we're using are actually pre-compressed. You see that I can hold the top of it and it doesn't weigh enough to stretch it out. So its equilibrium length is shorter than the physical length of the spring, not string, because they're pre-compressed. So these you can only stretch, but others you can make them so they go both ways. So potential energy is defined only for things that will return the work. And the definition of potential is actually defined as a change. The change in potential energy, I used U here for potential energy. Our textbook uses PE for potential energy. I imagine you'll get used to using PE since that's what our textbook uses. Speaking of textbooks, remember I mentioned that you could buy textbooks for $37.50 if you wanted. And Ryan got his textbook. That's what it looks like. Open it up so they can see that it actually looks like a textbook inside. So you have normal paper, full color printing. $37.50 is not a bad price. So if you want a printed textbook, I still went with an option that's going to save you a lot of money. So I'm feeling pretty good about that. I mean, $37.50 is less than the used book price you usually get, right? So, and remember, well, I talked about it before, but what are you going to do if you want to get a book like Ryan's? Yeah, talk to Terry Lara in the bookstore. Okay. Thank you, Ryan. I'm actually pretty excited that they weren't lying about the quality because I was skeptical. Okay, so with those potential energies, using that relationship that work is force times distance and the force of gravity, we can find that the gravitational potential energy is mass times the acceleration of gravity times the elevation. Now you notice here there's a plus constant. For kinetic energy there was a plus constant. For potential energies there's a plus constant. Only in the case of gravitational potential energy do we not always say, well, that plus constant, we're just going to set that constant to 0. With gravitational potential energy, we say, well, let us define this constant as minus mgy0 so that I could rewrite my potential energy as mgy minus mgy0. That means that I can choose a y0, our reference elevation for 0 potential energy. For other potential energies like the spring potential energy, we don't have for mathematical simplicity, we don't have the freedom to choose where we're going to set the 0 point. But for gravitational, because it's linear, we can choose that. So when you're doing a problem with gravitational potential energy, you could say 0 potential energy is here. You could say 0 potential energy is at the floor. I could say it's up here. Whatever's convenient. So when you look at, for instance, the last part of today's experiment, when I did mine, my gravitational potential was all negative. My kinetic energy and potential energy from the spring were all positive, and it looks kind of funny. It's just because of where I set 0 in the experiment. So we have that's gravitational potential energy. Finally, the spring potential energy. The equation for the force on a spring is shown here, using once again our definition of work is equal to force times distance. We can find the spring potential energy. As we'll talk about in class tomorrow, you actually have to use calculus, or we'll do it tomorrow in class graphically, to get the correct equation. If you just multiplied kx by x, you would get kx squared. And that's not right. It's 1/2 kx squared. And it comes from doing the calculus. So the potential energy for a spring is 1/2 kx squared. So the equations that you actually, the equations you actually need for today's lab are this equation here, this equation here, and it's changing pages for us. This equation here, this equation here. Yeah, I guess it's only 4. I'm not even requiring this one up here as a necessary equation. You just need those 4. And remember, you have to show what each variable means in your equations. I saw somebody who had lost points for not showing what those mean.
What was that other page?
The ones for gravitational and spring potential energies.
Is it the U's potential?
U's potential energy, yeah. One for spring and one for gravity. Well, for gravity, yes. Right there. Okay, now, for the experiment itself, we're going to have 3 parts. The first one is going to be measuring the spring constant. Oh, I forgot. You do need that equation because of part 1. So you also need force of the spring is equal to K delta X. So for the first part, you're going to take your spring carefully without getting it all out of whack. Just hang it from the handle of the drawer here. You might want to pull this out a little bit just to make it so it's easy to work with. Grab your meter stick and your masses. Okay, I'm probably going to break something if I do that. It'll be my meter stick and it won't be good. You have masses that are in the cupboards here. So I got meter stick and masses. And what you're going to do is hang masses and measure the length of the spring. So I'm going to measure the length from the top of the spring here to where the bottom of the spring is. Not, for instance, the bottom of the mass, because the masses have different lengths. And so it describes or prescribes for you what masses you're going to use here. It says hang 20 grams, then hang 40 grams. This here is 20 grams. So I'm going to start by hanging one of these, measure the length. Then I'm going to hook a second one on, hang it on it, measure the length. 20, 40. To get to 60, I have to take the 50 and the 10, 80, and 100. And you're going to measure the length of the spring for each one of those. When you've measured the length of the spring for each one of those, you probably have this as a question, what are you going to do next? You're going to graph it. So you grab yourself a piece of paper here and choose your X and Y axes. The vertical axis needs to be the force that you had hanging, so it'll be mg. The horizontal axis needs to be the length. Make sure you have your scale right, so you're going to have data that's going to fill the entire graph. Plot your points on there. Use a ruler to make the best straight line fit. and find the slope and y-intercept. And then you have some questions about how those relate to the spring constant. So I'm not going to answer them right now. I'm just telling you what you're going to do. So you're doing that to find the spring constant. So the point of this is to find the spring constant, just like it says. Once you've found that spring constant, then we're ready to do our static measurements. For our static measurements, you're going to have your cart set up like this. I'm not going to have the cart on the track. You're going to put it at a small angle, something like 10 degrees. I did bring out the angle indicators. We saw that these weren't perfect. Don't go to some crazy angle because yours says, oh, I'm only at 5 degrees. It's like this and I'm only at 5 degrees. I did my experiment somewhere around 6 degrees when I was doing this. So, you don't have to be 10 degrees. Just choose an angle. How do you get that angle? Well, you take Chad's briefcase and you put it under one end, right? Or something else, take Ryan's book, whatever. So you get that angle, and then probably the trickiest part of this is setting 0. You have at the low end of your track motion sensor, and you need to have one person hold the cart. So you're going to have the spring attached to the cart. It just goes in the little hole here at the end of the cart and then hooks on the end of the bumper. And you want one person to hold the cart so it's at the length that you found for the unstretched length of your spring from part 1. And then the other person is going to hit the button to 0 the sensor on your Data Studio. So let's look at how you do the thing for zeroing the sensor. So if all is good, you should see Data Studio pop up there. Notice, by the way, we have 2 tabs, one for static and one for dynamic. We're in the static now. You need to make sure you put your angle that you measured right here. So right now it says 0. Let's say I have 6 degrees, so I put 6 degrees in there. Say it was 6.3. Accept is what you're supposed to put, but after you change it, you can just move on. K, let's say I had K was 10.53. Notice the units are newtons per meter and degrees. So I put those in. Once I have them in, then it will know how to calculate things. So the first thing you do, the reason it starts with this open, is because you're going to put in those values for the spring constant and the angle that you have it at. So I'm done here. I'm just going to close the calculator and go to hardware setup. I don't have one here, as luck would have it. I don't think I can show you how to do it since I don't have one. I can show you what I would do. Okay, you saw I just clicked on the data summary and then on this gear next to the motion sensor. And down here there's a button that says 0 sensor now. And so all I'm going to do is when I have my partner holding it at the position where the spring length is what we said it should be for 0, I hit 0 sensor now. And that it'll tick a time or two as it sets, measures the distance and sets it. But that's all you need to do. So then you close this and you're ready to do your experiments. Any questions about how I got there or whatnot? Yes. So starting from here, I come over and click on where it says data summary. And then I have the motion sensor, and I click the gear in the line for the motion sensor. And then here's the button for 0 sensor now. So I just click it. Click it when it's at the right position. Right now it's doing nothing because I have nothing connected. All right. Then for this experiment, you're going to put masses in the cart. Now the cart already has a mass of 500 grams. And so we're starting with 500 grams, and you're going to add mass at 100 grams at a time. So you're going to release the cart. Don't let it swing back and forth. Just let it come down and use your hand to stop it, then let go and make sure it stays there stationary. So I'm doing this first with nothing in it. and it gets stationary, and then I'm going to come over here and see down here where it has the little grayed out preview. That should not be grayed out if everything's correctly connected. And you'll click there, you'll click there for preview to start. Then you'll click keep sample when you have it stationary. And that will fill in the first 2 points in this data table. Then you add 100 grams to it, let it come down and stop at its new position. When it's in its new position, you hit keep sample again, and it'll put in the second set of data. And so you're going to take your data, the stretch is how much you've stretched the spring. The elevation is saying, well, we have an angle theta. If it's moved this far, then the elevation change is the distance it's moved times sine of theta. So that's all that one is. It's the calculation based on the angle that you have told it you're using. So you're going to have those 2 pieces of data that you're recording up to putting 500 grams in the cart. Since the cart is already 500 grams, when you add 500 grams to the cart, that's this one. You're not using this one. When you add 500 grams to the cart, you have a total mass of 1,000 grams. That's the stopping point. One thing to be really careful of in this experiment is we don't want to stretch the spring so far that they are permanently deformed. So after doing that, make sure you write your data in your notebook. Right? Even though it's recording it here, write it in your notebook as you take it. And then you have some more, well, that was the wrong button to press. Oh well, it works. You have some more questions to answer about this. Actually, what is it? That says there's a graph. I swear there's no graph that it's automatically made. Oh, that's in the in the spreadsheet. I gotta check. I'm not certain that I made this part of the spreadsheet. Oh, yep, there it is. WorkEnergy Relation. Okay, so here you're going to put your data in. So you're going to put in your angle here, your spring constant here, and then your stretch length here, and it's going to do the rest of the calculations and plot your graphs. So that's the graph you're going to print. So to print this, you highlight that, and then you can, print. Print's over here. Print, and then you can choose to print to the Qt PDF to save as a PDF if that's what you've been doing, or you can print to that printer back there. Make sure you just select the graph. Don't print the whole spreadsheet. Okay, now moving on to the next part. Finally, the dynamic part. The dynamic part, you're just going to go back to the 500 grams on the cart and let it find its equilibrium position. Pull it down about, or actually, I think I said to pull it up so you don't go too far. Pull it up about 10 centimeters, and then have your partner start the timing here on the dynamic measurement. So you'll be on this one. And that data is completely bogus. You'll have your partner start the data right after you let go and just record it. It goes for, I think it stops automatically, but if it doesn't stop after 10 seconds, hit stop. And then you're going to analyze that data. Now, for today's lab, I want to have, for simple reasons, one of them being that I don't have a Physics 275 version of this that I prepared. We're going to all work in this room, so we'll have 4 groups of 3 and 6 groups of 2, which conveniently enough, everybody's already broken up into that, so just stay with your groups and you'll be good. Any questions about the experiment? All right, hit it.